Module 3, Kirchhoff's Laws. We'll begin our lesson with a basic discussion of network topology. Later on, we'll move to specific laws of networks called Kirchhoff's voltage law and Kirchhoff's current law. When we connect together electrical components with wires, we form something called a network. In an electrical network, every component is called an element. Elements are connected together by wires. The wires are shown in purple on the diagram below, and the elements are shown in green. The nodes and branches of a network are what define its basic interconnections. The interconnections between wires are called nodes. In the diagram shown below, the nodes are indicated by the red circles. The wire paths between nodes are called branches. Sometimes, adjacent nodes are connected only by wires with no elements in between. When two or more nodes are connected just by wires, the entire connection can be considered as one single node. Applying this concept to the network shown above reveals that it really only has three nodes: the single node in the upper left-hand corner, the two adjacent nodes connected only by one wire in the upper right-hand corner, and all three connection points at the bottom of the network comprise one big node. So there are three nodes altogether. Let's talk a little bit about how current flows through the branches of a network. Current can flow through any of the branches of a network. When depicting current flow on a network diagram, the direction of current flow is indicated by an arrow. In this network, current flows out of the positive terminal of the power supply and through the horizontal element located on the top branch of the network. This current is then split into two pieces, and each piece flows down and through one of the elements located on the right-hand side of the network. These two currents then combine and flow along the wire at the bottom of the network and back into the negative terminal of the voltage source. Note that the voltage sources in a network drive the flow of current through its various branches. We'll talk about this idea more later on in the module. Note that every current has both a value and a direction. The direction of the current is defined by the person drawing the network. Once the mathematical direction of the current has been defined, its value is determined by the physical properties of the circuit. Thus, if the direction of a current is defined in the downward direction, but the physical current flows upward, then the current as defined by the downward arrow has a negative value. In this example, the arrow above defines the positive current flow direction of I1 as downward in branch A. Let's suppose that 4 milliamps of current physically flow downward in branch A. Then I1 will equal 4 milliamps. Conversely, let's suppose that 4 milliamps of current physically flows upward in branch A. Then I1 as defined will equal minus 4 milliamps. Let's formalize our discussion of current flow by learning Kirchhoff's current law. Kirchhoff's current law can be stated in the following way. The sum of currents flowing into a node must be balanced by the sum of currents flowing out of the node. This law is a fundamental principle of physics and ultimately derives from Maxwell's equations of electromagnetics. Let's examine this principle in the context of the circuit diagram shown below. The red node is depicted in the upper right-hand corner of the diagram. The current I1 flows into the node, and the currents I2 and I3 flow out of the node. Again, in summary, I1 flows into the node, I2 flows out of the node, and I3 flows out of the node. Therefore, I1 is equal to I2 plus I3. In the previous slide, Kirchhoff's current law was written as I1 equals I2 plus I3. Note that we can do some mathematical manipulation and write that same equation in the following form. I1 minus I2 minus I3 equals 0. If we examine this form of Kirchhoff's law, we realize that it can be stated in the following formal way. The sum of all the currents that enter a node is equal to 0. In the example shown above, I2 and I3 leave the node, hence the currents minus I2 and minus I3 enter the node. Thus, the formal equation that states Kirchhoff's current law says that I1 minus I2 minus I3 equals 0, or the sum of all the currents entering the node is equal to 0. Let's illustrate Kirchhoff's current law with an example. Question: how much is the current I0 in the diagram shown below, given the values of currents shown by the blue arrows? The answer is that I0 is equal to 2.5 milliamperes plus 4 milliamperes, which when added together gives 6.5 milliamperes. Note that the shortcut expression for milliamperes is just milliamps. A milliampere is 1/1000th of an ampere. Note that a node need not be a discrete point, but can simply be any closed surface into which current flows in and current flows out. Thus, the dotted circle drawn around the left-hand vertical element can be thought of as a node, with 2.5 milliamps flowing in from the top, hence 2.5 milliamps must exit the node at the bottom. The same argument can be made for the right-hand vertical element in the network shown above, in which 4 milliamps flows in from the top, hence 4 milliamps must flow out from the bottom. Then applying Kirchhoff's current law to the bottom node reveals that I4, which is the current flowing back into the I0 source, is equal to I2 plus I3, or 6.5 milliamps. Here's another example of Kirchhoff's current law. Question: in the circuit diagram shown below, how much are the currents I1 and I2? It might be a good idea to pause the presentation and see if you can figure out the answers on your own before proceeding. Here are the answers. I2 is equal to 10 milliamps minus 3 milliamps, which is equal to 7 milliamps. This result can be computed by applying Kirchhoff's current law to the upper right-hand node of the circuit. 10 milliamps flows into the node, hence 10 milliamps must flow out, and with 3 milliamps flowing down the left-hand branch under the node, that leaves 7 milliamps that must be flowing as I2. Similarly, I1 must equal 10 milliamps plus 4 milliamps, or 14 milliamps altogether. Note that if we were to apply Kirchhoff's current law to the bottommost node of this network, we would have 4 milliamps coming in from the leftmost vertical element, 3 milliamps from the middle, and I2 equal to 7 milliamps from the right. Adding all these three currents together equals 14 milliamps, which is equal to I1. In this case, I1 flowing up into the negative terminal of the voltage source. A parting note on Kirchhoff's current law. As you may have noticed on some of the slides thus far, Kirchhoff's current law is sometimes abbreviated by just the letters KCL. Let's review the different ways that we can state KCL. 1. The sum of all currents entering a node must be 0. 2. The net current entering a node must be 0. Or, finally, whatever flows into a node must come out. We're now ready to move on to a more general discussion of networks and their various properties in the context of KCL. Let's now expand our general view of networks and show how KCL works in all of them. As we discussed before, a network is an interconnection of elements via nodes and branches. There are many kinds of networks that occur in technology and in nature. Each of these networks is defined by its elements, the purpose of the network, and its connection paths. An electrical network is made up of elements that are electrical components. The network in such a case is called a circuit, and the connection paths are formed by wires. A digital communication network is made up of elements that are computers. The network itself is called the Internet, and the various connection paths are formed by fiber optic cables. A biological network is made up of elements that are organs. The network is made up of the circulatory system, and the connection paths are formed by blood vessels. Other types of networks include electrical power distribution networks, automobile traffic networks, and water distribution networks. Kirchhoff's current law applies to all these kinds of networks. Let's look at KCL in the context of a fiber optic network. In this case, I stands for light intensity and not for current. The node in this case is a partially reflecting mirror, shown here in blue. The connection paths are fiber optic cables that come in from the left, leave from the right, and leave vertically downward. Let's define three beams of light in this system. The first is a light wave of intensity I1 coming in from the left. The second is a wave of intensity I2 leaving to the right, and the third a light wave of intensity I3 that exits the screen at the bottom. KCL for light could be written in the following way: I1 equals I2 plus I3. This law is consistent with the conservation of energy. A form of KCl also applies to the flow of human blood in blood vessels. In this case, F is used to depict the blood flow rate. The node in this case is an organ, and the conducting pathways are blood vessels. The flow rate F1 goes into the leftmost blood vessel and into the organ, and the flow rates F2 and F3 come out through the other blood vessels. Thus, KCl for blood flow could be written as F1 is equal to F2 plus F3. Let's move on to a new topic. We're going to apply the same type of analyses and description that we applied to current to the concept of voltage. It's important to remember that voltages are measured across the branches of a network, from one node to another. Sometimes people think of voltage as existing at a point, but that situation only occurs where one node has been designated as a reference node called ground. In that case, when we say that voltage exists at a point, we mean it exists between the node in question and the reference ground node. The direction of a voltage, sometimes called its polarity, is indicated by plus and minus signs on the circuit diagram. Remember that voltage sources are important because they drive the currents through the branches of a network, and hence determine the values of those currents in combination with the characteristics of the elements in the network. As was the case in our discussion of current, the polarity of a voltage is defined by the person who draws the network. The numerical value of the voltage is determined by the properties of the circuit. Here's an example. The plus and minus signs in the circuit diagram shown above define the polarity of V3 as positive when measured from node 1 to node 2. Now suppose that a positive value of 5 volts appears physically from node 1 to node 2. Then the designated V3 would be equal to 5 volts. Let's suppose, on the other hand, that plus 5 volts appeared physically from node 2 to node 1 because of the properties of the circuit. For example, if the polarity of the voltage source on the left were reversed. In this case, V3 as defined would be equal to minus 5 volts. Kirchhoff's voltage law is also a fundamental principle of physics that derives ultimately from Maxwell's equations. It states the following: the voltage measured between any two nodes in a circuit doesn't depend on the path taken. This concept is best illustrated by example. Let's look at the voltage between the two nodes shown by the red arrow. The voltage between these two nodes, as depicted on the left-hand pathway, is equal to V1. We can also add together the two voltages V2 and V3 that appear on the right-hand side of the red arrow, and these also will equal to the voltage. So we therefore conclude that V1 is equal to V2 plus V3. We can do the same thing with the second red arrow that points between the two nodes in question. If we take the pathway depicted by this second arrow, then the net voltage between the two nodes is equal to V2 plus V4. We thus conclude by Kirchhoff's voltage law that V1 is also equal to V2 plus V4. By following the pathway of the third red arrow and the two nodes to which it points, we can also conclude that V3 is equal to V4. because these voltages both appear between the two nodes in question. Let's take the statement of Kirchhoff's voltage law from the previous slide, V1 equals V2 plus V3, and restate it in a more formal way. This same equation can be written as minus V1 plus V2 plus V3 equals 0. Thus, a formal statement of Kirchhoff's voltage law can be expressed as follows. The sum of voltages around a closed loop is 0. Note that this law can be applied to any closed loop in the circuit. The polarities of the voltages enter into the equation according to the first sign that the arrow encounters. Thus, the left-hand loop in the circuit in this diagram shows that minus V1 plus V2 plus V3 equals 0. A closed loop drawn around all of the outer branches of the network would yield the following statement of KVL: minus V1 plus V2 plus V4 equals 0. Let's review the formal definition of KVL and how you use it, as discussed briefly on the previous slide. The formal definition says that the sum of voltages around a closed loop is 0. Here are the steps for applying this law to any given circuit. First, you have to define an arrow in some direction around the closed loop about which you want to calculate KVL. Next, you sum the voltages as they are encountered in going around the loop. It doesn't matter where you start in the loop, because all the terms representing the voltages will appear on the left-hand side of the equation. If the arrow first encounters a plus sign for any given element, then the voltage representing that element is entered into a plus sign into the KVL equation. Similarly, if the arrow first encounters a minus sign for any given element, then the voltage across that element is entered with a minus sign into the KVL equation. Thus, for the arrow shown above, we arrive at the following equation: minus V1 plus V2 plus V3 equals 0. We can also draw an arrow around the outer loop of the circuit. For variety in this case, we've drawn the arrow in the counterclockwise direction. It doesn't really matter. It just means that the different voltage terms in KVL will have their signs reversed. The equation will still be true. In this case, KVL is written as minus V4 minus V2 plus V1 equals 0. As an exercise, you might want to try writing the KVL equation for this outer loop with the arrow going in the clockwise direction. In this case, the answer will be minus V1 plus V2 plus V4 equals 0. That's the same equation as the one drawn here on the screen. Let's illustrate this concept by way of an example. Question: given the information shown on the circuit diagram below, what is the value of the voltage source V0? You might want to press pause for a moment to give you time to figure out the answer. Here's the answer. V0 is equal to 3.1 volts plus 6.8 volts. We arrive at this result by applying Kirchhoff's voltage law to the two nodes to which the voltage source is attached. Another easy question: how much is the voltage V4 in the circuit diagram shown above? The answer is trivial. Because the two rightmost vertical circuit elements are connected to the same nodes, their voltages must be the same. So V4 is equal to 6.8. Here's another example. Question: in the circuit diagram shown below, if the voltage source V1 is equal to 10 volts, and we know by measurement that V5 is equal to 2 volts, what are the values of V2, V3, and V4, given the polarities of the voltage symbols as drawn on the circuit diagram? Again, you might want to press the pause button for a moment to give you time to figure out the answers. Here are the answers. Applying Kirchhoff's voltage law to the two nodes to which the voltage source V1 is connected reveal that V2 is equal to V1. This is a rather trivial result. If we apply Kirchhoff's voltage law to the voltages V3 and V5, we know that the sum of those two voltages also has to equal 10 volts. Hence V3 is equal to 10 volts minus 2 volts, or 8 volts. And finally, the voltage V4 can be found by a trivial application of Kirchhoff's voltage law. In this case, V4 is equal to V5, or also 2 volts. Okay, let's summarize what we've learned in this module. An interconnected set of electrical components is called a network. A network consists of nodes and branches. Kirchhoff's current law states that the sum of all the currents entering a node must be 0. This law can also be expressed in the following way: whatever flows into a node must come out of the node. Kirchhoff's voltage law states that the sum of voltages around a closed loop in the network is 0. This law can be summarized also in the following way: the voltage measured between any two nodes in the circuit is independent of the pathway taken.